Thank you. Thank you all. Thank you very much for coming. And, oh, it's a little loud. I wonder if I could turn that down. It's okay? I'm going to stand up here, and I don't want feedback, so we'll see. Okay, we're not getting feedback yet. You want to make a bet? Okay, good. Anyway, thanks for coming. Yes, I heard the university bookstore wouldn't bring books, so you should buy books on Amazon.com, not at the university bookstore. In any case, it's a pleasure, as I say, and I'm sorry that some people over there are in the overflow room, but as pointed out, I will be answering your questions first. I put these quotes up here so you'd have something to read when I was being introduced. But this is actually probably particularly appropriate. It's one of my favorite quotes from Lise Bogan, but it really epitomizes what I want to talk about, which is, and one of the reasons I run an institute called the Origins Project is that really the interesting question is how did you get to the starting point? And that's pretty well true for all of science. The most interesting questions are origins questions, and I will talk a lot about origins today in terms of the universe. Now, in fact, the question, well, by the way, this is a globular cluster. It's a beautiful night sky. The stars are beautiful. I used to live in Cleveland, and I used to have to tell people that these were stars. But I've been in Vancouver for a little over a week, and I guess I would have thought I would have to tell you the same thing. But I was gone one day. It was sunny. In any case, as beautiful as that is, as was pointed out, the night sky is indeed beautiful, but the really important stuff, it turns out, is the stuff between the stars, the stuff you can't see, as I'll talk about. And it's changed everything about the way we think about the universe, from its origin to its future, and the present as well. Now, the question that I do want to deal with, because it does relate to the new book, is a key question that's been around for as long as people have asked questions. Why is there something rather than nothing? It's often been taken to be a religious question or a philosophical question, but it is neither. It is a scientific question. Because something and nothing are physical quantities, and therefore they're the domain of science. And science has completely changed the way we think about this question. And as I'll talk about, the philosophers and theologians have very little to add. Well, they didn't add anything in the first place. But anyway, now there's a number of different ways to answer this question, and this is the first way. But that doesn't tell you anything. It doesn't explain anything. It's just intellectually lazy. It just relies on a story made up by people, written down before anyone even knew the Earth orbited the Sun. But it certainly doesn't explain anything. It's a nice story, but it doesn't predict anything. It doesn't tell you how the universe evolved. So as I say, I want to go back. The story I want to tell you is based on actually looking at the real universe, the universe we live in, and trying to force our beliefs to conform to the evidence of reality rather than the other way around. So I want to begin this mystery story a little bit differently. So let's begin. It was a dark and stormy night. Now, I'm not referring to the origin of the universe here. I'm talking about the night that Albert Einstein dotted the last period on his greatest theory, the theory of general relativity. It was the theory of gravity, but more importantly, it was the first theory that was not just a theory of how things move through space, but in fact, a theory of space itself. In fact, he showed that space was dynamical. It could respond to the presence of matter and energy. And because it was a theory of space, it was the first theory that could really be a theory of the universe. And he knew that. But he was very disappointed by a simple fact. It turned out not to describe the universe in which we lived. Nowadays, that doesn't bother physicists so much, but it used to. And Einstein worked very hard to try and change the theory to be in accord with the universe in which we lived. You see, because the problem is, in 1916, when Einstein developed general relativity, the universe was static and eternal, as far as science was concerned. The conventional wisdom was that the stars and galaxies, well, stars, in fact, had been around forever. If you look at the night sky, it's more or less the same day after day. And it would always be that way. Now, there is a problem, and there's a problem with not just general relativity, but Newtonian gravity. And any of you who've taken physics, which is all of you, I assume, know that gravity sucks. It always pulls, it never pushes. And you can't have a static universe if gravity sucks, because you put stars out there, and they'll eventually always collapse together. And so Einstein realized that, and he revised his equations a little bit. And I've written them down here, and we're locking the doors in both this and the overflow room now. And I've written them down here. So, but I first put them in user-friendly fashion. This is for the biologists. There we go. It's not completely facetious, but we're all okay with this. The left-hand side equals the right-hand side. People are comfortable. Okay. In general relativity, it really means something because the left-hand side of the equation relates to the geometry of space, because matter can curve space and therefore produce interesting geometry. So the curvature, all the geometric terms are related to on the left-hand side, and the stuff that produces the curvature, the energy and momentum of the universe, is on the right-hand side. So energy and momentum produce curvature, which affects the evolution of energy and momentum, and that's Einstein's equations. And now I'm a theoretical physicist, as was pointed out, so I have to write down the Greek letters, and that's much more illuminating to many of you, I'm sure. But this is the problem. This is the theory in which gravity sucks. And this was the theory that didn't describe the universe. So Einstein realized that consistent with the mathematics that had led him to develop general relativity, with the symmetries, he could, in fact, add an extra term, a new term on the left-hand side of his equations, which he called the cosmological term. And this term would produce a small repulsive force throughout all of empty space. So small that you wouldn't notice it here on Earth, and it wouldn't affect any of the wonderful calculations that led Newton to understand the orbits of the planets around the sun. It wouldn't affect any of that. But it could build up so that on the scale of our galaxy, that small force could finally hold apart distant stars, and he thought that could produce a static universe. Now the problem was, there was a problem, and in fact, very shortly after he wrote down the equations, it began to be realized that the universe wasn't static. And in fact, when I was on leave a few years ago in Switzerland, I got a postcard from Einstein to Hermann Weyl, who was a very famous mathematical physicist. And some of your German is better than mine, but this was, if you get rid of a quasi-static universe, then out with the cosmological term. Because he realized that if the universe wasn't static, you didn't need this repulsive force anymore. Because if the universe was expanding, gravity could be purely attractive and slow the expansion. And the big question of 20th century physics, the holy grail of 20th century physics, became, is there enough gravity to stop that expansion and cause the universe to collapse in reverse of the Big Bang, a big crunch? And the big question became, is the universe going to end with a bang or a whimper? And so he realized it was no need for that term, and he said it was his biggest blunder, and he wished he'd never introduced it. Now, even though this was from 1923 already, but the person that convinced the world that the universe is expanding came later, and he's one of my heroes because he gives me great faith in humanity. This is Edwin Hubble. He began life as a lawyer and then became an astronomer. And so there's hope for everyone. And Hubble did several amazing things. The first amazing thing he did, which is somewhat peripheral to what I want to talk about, but nevertheless it sets the framework. Up till 1925, when he worked with the Mount Wilson telescope, if you look through telescopes at our galaxy, you saw these little fuzzy things. And up to that point, our galaxy was it. The universe was our Milky Way galaxy. And you looked at our galaxy, you saw these fuzzy things. They were called nebulae, which is Greek for fuzzy thing. And when you saw them, you didn't know, there was a big debate about what they were. But in 1925, with the Mount Wilson telescope, he was actually able not only to distinguish individual stars in these objects, but to show that there were other island universes, other galaxies. And we now know that there are over 400 billion galaxies in the observable universe. 400 billion, and a single human lifetime ago, 87 years ago, we knew of one. So it's not too surprising that we're surprised. We're like the early map makers, just beginning to understand the universe on the largest scales. And it's remarkable, and I want to celebrate those revolutions in our understanding today. So Hubble was the one who convinced the world that the universe was expanding. And how did he do that? Well, he looked out with his telescope. These are not sperm, these are galaxies, by the way. And this is us. And what he did was he looked out at galaxies. He saw that on average, all the galaxies were moving away from us. And in fact, those that were farther away were moving faster. Those who were 2 times as far away were moving 2 times as fast. Those that were 3 times as far away were moving 3 times as fast, and so on. So what does this tell you? Well, it's obvious. It tells you we're the center of the universe. It's obvious. Just look at it. Well, as some of my friends remind me on a daily basis, however, that's not the case. In fact, it tells us that the universe is expanding uniformly. Now, why is that, and why is it so hard to tell? Well, the thing is, we're stuck in our universe. Well, most of us are. The Republican candidates aren't, but the rest of the world is. But yeah, you can. Okay. That's an easy laugh. This is Canada, so it's easy. But anyway, if we want to see what this really implies, we've got to get outside of our universe, which we can do not easily in our own universe, but I can make a universe where you can look outside the box. And here's the universe that I can create. It's two-dimensional. We can stand outside of it. And here are a bunch of galaxies, a part of the universe, and I put them at regular intervals. And at some time t1, here they are. And you can see at time t2, the whole bit of the universe is bigger. The galaxies have moved apart. So if you were standing outside that universe, it would be obvious that the universe was expanding. But what would it look like if you lived in that universe? Well, pick a galaxy, any galaxy, say that galaxy. And to see what it would look like, I just have to superimpose this image on top of itself, placing that galaxy on top of itself right there. And what do you see? You see exactly what Hubble saw. Everything is moving away from you, and those that are twice as far away have moved twice the distance in the same time. Those that are 3 times as far away have moved 3 times the distance, and so on. And it doesn't matter what galaxy you pick. Any galaxy, you see exactly the same thing. So, depending upon your mood, either every place is the center of the universe or no place is the center of the universe. It doesn't matter. What really matters is that the universe is expanding. And that changed everything, because it meant the universe had a beginning. And that had profound implications for science as well as theology. The universe had a beginning, which we now know is 13, well, except in Arkansas and Ohio and a few other places, we now know is 13.72 billion years ago. And it's amazing to me that we know that number to that accuracy, as I'll talk about. Now, this is so important for what I want to talk about that I want to tell you how we know this. Because Hubble, this is physics, so you measure things. And Hubble saw that the velocity of distant galaxies was proportional to their distance. So that means you have to measure velocity and distance. So how do we do that? Well, velocity turns out to be the easy part. These 2 cowboys on the plain know how to, in the prairies, they know how to do that. They're looking at this train, and one says to the other, "I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect." And what they're talking about is the well-known fact that as a train is coming towards you, the whistle sounds higher, and as it's going away from you, it sounds lower, and that's because the sound waves get scrunched up in front of the train and stretched out behind the train. Now, it turns out for very different reasons, the same thing is true for light. So when we look at distant galaxies, if the light is stretched, they're moving away from us, and by the amount by which the light is stretched, you can tell how fast. Now, the long wavelength end of the visible spectrum is the red end of the spectrum, so we say those things are redshifted. And the greater the redshift, the greater the velocity. So what Hubble discovered is that objects that are progressively further away from us are moving away from us faster with a bigger redshift. But that's the redshift. How does he know the distance? How do you know that they're progressively further away from us? That's the hard part. That's always been the hard part in cosmology. Because we don't have tape measures that are that long. We can't measure distance directly, so we have to figure out a way to indirectly measure distance, and that's the problem. How do we do it? Well, of course, we use the laws of physics. I could measure the distance to the back of the room by turning out all the lights here, except for one of the lights in the back that might be 100 watts. And then if you're as old as I am, you remember cameras when they had light meters. And if I had a light meter here, and I knew that was 100 watts, and I received 1 watt of light into my camera, then I know how fast light spreads out, or how it spreads out over space. I could work backwards from 1 watt. If I knew it was 100 watts, I could work backwards and find the distance to the back of the room. So if the universe were populated by 100-watt light bulbs, we'd all be fine. But it's not, so we have to find the equivalent. We have to find something we call a standard candle, something whose intrinsic brightness we understand, and then we look at it through a telescope, we see how bright it looks, and we know how far away it is. And that's the hard part. And in fact, it's so hard that this is Hubble's original data from 1929. And this is velocity versus distance, so we saw that it was increasing. This is one of the reasons he was such a great scientist, too. He knew to draw a straight line through that data set. Not at all obvious. He also did something very important for the rest of us. He got the answer wrong by a factor of 10. And astrophysicists have been trying to emulate that ever since, in fact. But But it was profoundly significant because if he found that the universe was expanding 10 times faster than it actually is. And if you work that through, if you know how fast the universe is expanding, you can figure out how old it is, because you can figure out how long it took objects to get out to where they are. And if the universe were really expanding at this rate, the universe would be 1.5 billion years old, which was a problem even in 1929 when this data was published, because again, except for Arkansas and Ohio and a few other places, we knew the Earth was older than 1.5 billion years old. So it was really embarrassing that the Earth was older than the universe for most cosmologists. And of course, and what's interesting about science is that if that had worked out, that would have been a real problem for the Big Bang. And we would have had to rethink things. But of course, he got the answer wrong. We now know it's about almost 10 times smaller, and the universe is 13.72 billion years old. Now, we can do better now because we have a new type of standard candle. And here it is. This is one of my favorite Hubble Space Telescope pictures. Well, they're all my favorite, actually. But this is a galaxy long, long ago and far, far away. It's not that far away, actually. It's only about 50 million light years away. So it takes 50 million years for the light from that galaxy to get to us. And it's a spiral galaxy like our own. Once you've seen one, you've seen them all, more or less. And this galaxy contains about 100 billion stars, as our galaxy does. And you notice something strange here. The center of the galaxy here contains about 10 billion stars. And this star here is as bright as the whole center of that galaxy. Now, how can that be? Well, the first assumption would be that it's just a star in our galaxy that got in the way of the picture, which would be a good assumption, but it's wrong in this case. It actually is a star at the edge of that galaxy. And it is burning with a brightness of 10 billion stars. How can that be? It's a star that's just exploded. The greatest cosmic fireworks around, a supernova. And when stars explode, they briefly shine with a brightness of about 10 billion stars for a period of about a month. Now, these turn out to be wonderful standard candles. Now, the problem is that stars don't explode very often. Well, it's actually good news for us for the most part. But it's actually important for us that they explode, because you wouldn't be here if they didn't. Because it turns out every atom in your body, essentially every atom in your body, was once inside a star that exploded. Maybe more than one star. Because you see, in the Big Bang, the only elements that were created in the Big Bang were hydrogen, helium, and a little bit of lithium. But well, for some of you, lithium is important. But for the rest of you, carbon, nitrogen, oxygen, iron, all the stuff that makes your life livable, those elements weren't created in the Big Bang. The only place they were created is in the fiery core, nuclear furnaces in the cores of stars. And the only way they could get into your body is if the stars were kind enough to explode. And in fact, over the history of our galaxy, about 200 million stars have exploded. And so it is true that every atom in your body was in at least one of them. And the atoms in your left hand may have been in a different star than your right hand. You are literally star children. You're stardust. It is, without a doubt, in my opinion, the most poetic thing I know about the universe. You are star children. And that's all peripheral, but it's so nice I couldn't resist. But these supernovae occur once every 100 years per galaxy. So how can we study them? That's the problem. Well, it's simple. We assign a graduate student to each galaxy. 100 years is about the right time for a PhD. Graduate students are cheap. If they die, you just get a new one. It's really easy. But we don't have to do that, actually. We rely on another fact which most people don't realize, and it's important. Is the universe is big and old, and that means rare events happen all the time. And if you took went out on a rare, clear night here and held your hand up to the sky and held a dime-sized hole in there and held it up to a dark spot of the sky where there are no galaxies, no stars, no nothing. With one of the largest telescopes we have on Earth today, if you looked in that region, you could see 100,000 galaxies. And if you think about it, once per 100 years per galaxy, 100,000 galaxies, on a given night, you'll expect to see a few stars explode. And astronomers do that. They apply for telescope time, and on a given night, they'll see some stars explode. And that means we can study them. And here we can take movies of them before they explode and afterwards, and this will repeat. So this is a star that's going to explode in this galaxy. We can measure its brightness over the course of time. Most importantly, we can measure its colors, because those colors tell us it's a particular type of exploding star called the Type 1a supernova. And it turns out, for reasons I don't have time to explain here, that Type 1a supernovae are great standard candles. They're such good standard candles, in fact, that we can use them to study the expansion of the universe. And in fact, they're such good standard candles that the people who used them won the Nobel Prize in Physics this year just for doing that, as I'll talk about. Okay. In fact, we can use them to make a much better Hubble plot than Mr. Hubble could. This is after the profound realization that on a log-log plot, everything looks like a straight line. But even without that guide to the eye, we can now measure the Hubble constant, the expansion rate of the universe, not to a factor of 10 uncertainty, but to 10% or 5 to 10% accuracy. So we know how fast the universe is expanding. We've got that down, finally. And then the next question is what will happen to that expansion? And in fact, actually, that's the reason I got into cosmology. My background's in elementary particle physics, but I realized, as I'll talk about, that I could use those ideas to maybe to be the first person to know how the universe would end, which seemed like a good idea at the time. So I got into the field. And the reason that is the case that if we're going to determine the future of the universe based on how it's expanding now, we need to know about the gravitational pull that's slowing down the expansion. And it turns out, as I told you, general relativity tells us that space is curved in the presence of matter. Now, I can't draw curved three-dimensional spaces because we're three-dimensional beings. But I can draw curved two-dimensional spaces, so you can see these. But these are just guides to the eye. Our universe is three-dimensional. But it turns out that our universe can exist in one of three geometries, so-called open, closed, or flat. And I can picture them if they're two-dimensional. They're harder to picture if they're three-dimensional. But I can tell you what they'd be like. For example, in a closed universe, if you looked far enough in that direction, you'd see the back of your head. Light would go around the universe and come back. Okay? And all that sounds nice, but what's really important is in a closed universe dominated by matter, the universe will expand, slow down, and stop, and recollapse. In an open universe dominated by matter, the universe will keep on expanding forever. And in a flat universe, it's just the boundary between the two. The universe will expand and slow down, and never quite stop. And therefore, if we're going to know the future of the universe, we just have to know which universe we lived in, I thought. And therefore, if I could determine the geometry of the universe by how much matter there was, I would be the first person to know how the universe could end. How can we determine how much matter there is? Very simple. You weigh the universe. It's easy. How can you do that? Well, I wrote a whole book about it once, but it turns out that I can show you a simple way because now we've done it. And I want to give you a little history lesson here because I want to take some of you back to a kindler, gentler time. This was 1936, and this is the journal Science, a prestigious scientific journal. And there's an article that was written in 1936 called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. Okay. But this is how the article began. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I'd made at his request. This note complies with his wish. Try and publish that nowadays in Science magazine. You wouldn't get in. Now, it turns out the author had some credentials. His name was Albert Einstein, so they maybe gave him a little leeway. But what he published here was a calculation that he thought was incredibly irrelevant and unimportant. He had already shown that light could bend in the presence of matter, and then he realized that if you have a big enough mass and you have a light source behind the mass, the light can go around it, bend, and come back, and be magnified as my glasses magnify things. So space can act like a lens. Or if you had like a cut glass goblet, and I looked in this room now, I'd see lots of different images of all of you. And he realized that space could do that, but he said it would never be observable. He just thought the effect was so small, it'd be never observable. He thought it was an irrelevant calculation. This is the calculation from his notebook in 1936. And he thought it was so unimportant that he actually forgot that he did exactly the same calculation in 1912. If you look at his notebook there, you see exactly the same calculation. But he'd ignored it because it was so irrelevant. And I really liked the way he wrote to the editor after it was published, and he said, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." That's how science is done. Now, it turns out it is more than of a little value because we use it to weigh the universe. And here's a picture of the thing that Einstein said we'd never see. This is another Hubble Space Telescope picture. It's a cluster of galaxies. Clusters of galaxies are the biggest bound objects in the universe. They're about 10 million light years across, and almost all galaxies live in clusters. And because they're the biggest objects, anything that can fall into anything will fall into a cluster. And therefore, if you can weigh the cluster, you can weigh the universe. Now, by the way, in this picture, I should point out that every dot is a galaxy, not a star. And every one of these galaxies contain about 100 billion stars. And this cluster is 5 billion light years away from us. That means the light from these galaxies left the galaxies 5 billion years ago, before the Earth and Sun even formed. And many of the stars in this picture no longer exist. And the civilizations that may have existed around those stars no longer exist. Every time I look at a picture like this, I'm inspired. It's kind of amazing to think of how, as I'll talk about, of how insignificant we are. But you don't have to be a rocket scientist, however, to realize there's something strange in this picture, and that's these weird blue things. These objects, in fact, are multiple images of a single galaxy located 5 billion light years behind that cluster. And space has produced a lens. It's magnified the galaxy, it's distorted it, it's produced multiple images. They're all images of precisely the same object. So this is proof that space is curved, if you want. And it's wonderful, but now we can turn it around. We know general relativity works, so we can work backwards and say how much mass is in this system and where is it distributed so you can produce that image. It's a complicated mathematical thing called an inversion, but we can do it. And we do it, we get the following image. So this is a picture of where the mass is in that system, and the spikes are where the galaxies are. But what you notice is most of the mass in the system is where the galaxies aren't. There's 40 times as much mass in this system as meets the eye. Most of the mass is where the galaxies aren't, and physicists, because we're so creative, call that dark matter, because it doesn't shine. And what we've discovered is not just in this cluster, but in all clusters, and in fact in galaxies themselves, 90% of the mass of stuff in the universe is dark. It doesn't shine. And what makes that interesting is it turns out there's so much of it, we're reasonably certain that it's not made of the same stuff as you and me. Because we know how many protons and neutrons are in the universe, it turns out, for reasons, again, I won't explain. And there's about 10 times more stuff here that can be accounted for by all the protons and neutrons in the universe, the stuff that makes you up. So we think that dark matter is some new type of elementary particle, which makes it interesting because it's not just up there. It's in this room. It's going right through your bodies as you nod off during this lecture. Okay? And that means we can do experiments here on Earth to look for it, not on the surface of the Earth, but we go deep underground. Places like the Sudbury Neutrino Observatory, say. Why? Because the Earth is bombarded by cosmic rays, and they get stopped, but we think these dark matter particles interact so weakly, they go right through the Earth on average without knowing it was there. And if you build a detector deep underground, you might have a chance of interacting with one of those objects. And there are detectors like that being built all around the world. In fact, I'm pleased to say about 25 years ago, I proposed the detectors that are now being used to do that. And one of them, any day, might discover the dark matter particles and discover what is the identity of this stuff that makes up most of the universe. But there's another way we may find out about it because, well, these dark matter particles were created around the beginning of time, and we could detect them. But there's another way you could actually try and produce them. If you had a machine that recreated the conditions at the beginning of time. And we have such a machine. It's called the Large Hadron Collider in Geneva. It turned on. It didn't make a black hole that destroyed the world, but it reproduces over a very small region conditions appropriate to the very early universe, so we may actually create those particles in the lab. So it's a race between the dark matter detectors underground and the Large Hadron Collider to see who might discover the nature of dark matter. But it turns out for our purposes, it doesn't matter what it's made of. How much of it is there? Because when we know how much of it there is, since it dominates the mass in the universe, we can weigh the universe. And we have now done that. After 80 years of trying, we know the answer. And here it is. I heard a gasp. Well, actually, when physicists find something important, they always give it a Greek letter because we want to sound scholarly. And this is omega. And omega is the ratio of the total amount of mass in the actual universe divided by the amount you'd need to make a flat universe. If omega is less than 1, there's not enough matter to make a flat universe, so it's an open universe. If omega is greater than 1, it's a closed universe. If omega is equal to 1 exactly, it's a flat universe. And therefore, we have discovered with no ambiguity that we definitively, according to this, don't have, by a factor of 3, there's 3 times too little matter to make up a flat universe. We live in an open universe, case closed, story over, great. Well, not great. Because it turns out we theorists knew the answer. We always know the answer. We're rarely right, but we always know the answer. And we knew that the universe was flat. We knew it was flat because it's the only mathematically beautiful universe. And these damn observers were coming up with the wrong answer, as they usually do. And it was really discouraging for us. But of course, this is a very indirect way to measure the geometry of the universe. You measure the expansion rate, and you find out the total amount of matter, and you put it all in Einstein's equations, and you see what the universe is going to do. But wouldn't it be better to measure the geometry of the universe directly? And we can now do that in the last decade or so. And I would have never thought it was possible, actually, to do. Well, actually, it turns out I actually wrote a paper on it 20 years ago, but I forgot I wrote it. But how can you measure the geometry of the universe directly? Well, let me ask you a simpler question. How could you measure the curvature of the Earth if you couldn't go into a satellite around the Earth and you couldn't go around it? It's very simple. You draw a triangle, and then you ask a European high school student, what's the sum of the angles in a triangle? Or maybe a Canadian high school student. You don't ask an American one, I know that. And they'll tell you it's 180 degrees. And then you say, that's fine, but you learned your geometry from Euclid. On a sphere, I can do something a little bit different. I can draw a triangle this way. I can go along the equator. I can make a 90-degree angle, go up to the North Pole, and make another 90-degree angle, and come back down to the equator. And I have a triangle with three 90-degree angles. 3 times 90 is 270. That tells me I'm not on a flat surface. So if you could draw a big enough triangle on the surface of the Earth, you'd know it wasn't flat. Well, it turns out this mathematics works out not just for curved two-dimensional surfaces, but for curved three-dimensional surfaces. And if we could draw a big enough triangle in a curved three-dimensional space and measure the angles, we would measure the geometry of the universe directly. And we have been able to find such a triangle, but again, just in a little over the last decade, by using the most important observable in cosmology, the cosmic microwave background radiation, the afterglow of the Big Bang. It was discovered by accident in New Jersey, of all places, by two people that didn't know what the hell they were doing. But they won the Nobel Prize anyway, because you don't have to know what you're doing to win the Nobel Prize. You just have to be lucky. And sometimes. You just have to make an important discovery, and they did. They discovered the afterglow of the Big Bang. So what's this stuff? Well, if we're in the Earth here and we look out at galaxies that are 1 billion light years away, we're looking back 1 billion years in time, as I've told you. So we're really doing cosmic archaeology when we look out at the universe. Now, if the universe is 13.7 billion years old, you'd think if you looked out far enough, you'd see the Big Bang. And in principle, that would be true. But we can't see all the way to the Big Bang for the same reason I can't see outside this room. These walls are opaque. And if I look out at the universe, I look earlier and earlier times, it was hotter and hotter and hotter. And when it was only about 100,000 years old, the temperature of the universe was about 3,000 degrees. And at that temperature, the dominant stuff in the universe, hydrogen, gets broken apart by radiation into protons and electrons. And every time it tries to combine, it gets broken apart again. So matter is no longer neutral before this time. It's what we call a plasma of charged particles. And plasmas are opaque to radiation. You can't see through them. So the universe is opaque back at these early times. So if I run the film forward, it's opaque, 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 and then boom, it cools down to 3,000 degrees. Protons capture electrons. Matter becomes neutral. And then it's transparent. So just like I can see the wall, my laser on that wall there, it's because the light gets absorbed and re-emitted by atoms on the surface of the wall, but the air between me and the wall is transparent, so I can see all the way back to it. So one of the predictions of a Big Bang is that there should be radiation coming at me from all directions from this what's so-called last scattering surface, and the radiation will have cooled from 3,000 degrees now to 3 degrees, and that's the radiation that these observers discovered by accident in New Jersey. Actually, many of you are old enough to have seen it yourself. I should point that out, because you're at least as old as me. In the days before cable TV, do you remember those? Some of you do. TV stations used to end, and then there'd be a test pattern, and then there'd be static. 1% of the static on your television screen is radiation left over from the Big Bang. So disconnect the cable tonight, free yourselves, and then look at the radiation from the Big Bang. It's kind of amazing. Now, on this surface, one important distance scale occurs. This distance here, it's spanned by 1 degree. This distance corresponds to 100,000 light years. Now, if the universe is 100,000 years old, and this is 100,000 light years, Einstein tells us no information can propagate faster than light. And that means that nothing that happened over here at that time could affect anything over there, because light can only travel that far. But it also means if I have a lump of matter, say, that's this big, it starts to collapse due to gravity and heat up and all sorts of things happen. But if I have a lump that's this big across, it doesn't even know it's a lump because gravity can't travel across it in the age of the universe. So it's like Wile E. Coyote, if you remember the cartoons. He goes off the cliff and he sort of stands there for a while before he realizes he's supposed to fall. That's the case with these big lumps. They won't start to collapse. So the biggest lumps that will have started to collapse significantly are this big across. And that gives us a triangle. It's a triangle a known distance away from us where one length of it is 100,000 light years across. And in a flat universe, what really defines a flat universe is light rays travel in straight lines. So if we ask what angle that will subtend on our eye, a 100,000 light year across ruler, it will subtend an angle of 1 degree. But in an open universe where light rays diverge as you go back in time, the ruler will look smaller. It will subtend only that angle. It'll look like half a degree. So the ruler will actually look smaller. In a closed universe where light rays curve inward as you go back in time, the angle spanned by that ruler will be bigger. It'll look like maybe 2 degrees. So all we have to do is take a picture of those lumps in the cosmic microwave background radiation and ask, are they half a degree, 1 degree, or 2 degrees? And we can directly measure the geometry of the universe. And that's what we've been able to do. This was the first experiment that was able to do it significantly. It's called the Boomerang Experiment in Antarctica, and it was a balloon and a microwave radiometer sent way above the Earth's atmosphere, and it went around the world, which is easy to do in Antarctica. If you at the South Pole, you do this, just like this. But they weren't quite there. They were at McMurdo, and it took about 2 weeks for this balloon to go around, came back to where it started, which is why it's called the Boomerang Experiment, and it looked at a small region of the sky and measured very accurately the microwave radiation coming from the Big Bang, and this is an image of the data it returned, a false color image, but nevertheless an image. These are the lumps, the hot spots and the cold spots in the microwave background radiation. That later, by the way, this is a baby picture of the universe. This is how it looked when it was 100,000 years old. And these are the lumps that would later collapse to form all the galaxies and stars and planets and aliens and everything. But what we care about here, I've superimposed it on this image just to give you a sense of scale, is we ask how big are those lumps? And to do that, well, we can draw a universe on a computer, and here's the actual image again in different colors. And these are universes we create on a computer, a closed universe, a flat universe, and an open universe. And you see in a closed universe, the average 100,000 light year across lump should look that big to us. But that's bigger than these lumps. And in an open universe, the average 100,000 light year across lump should look about that big. But that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. In fact, we now know to an accuracy of 1% that the universe is flat. So we pat ourselves on the back. But there's a problem, if you've been awake. Some of you have, I noticed. 10 minutes ago, I showed you that there's only 1/3 as much matter as you need to make the universe flat. That's a problem, because the universe is flat. We're missing 70% of the mass energy of the universe. Where could it be? Well, if it isn't where galaxies are, it must be where galaxies aren't. But what is where galaxies aren't? Nothing. Okay, let's go back to Einstein. He said it was his biggest blunder. He wanted to throw out the cosmological term. But the problem is it's kind of like putting the toothpaste back in the tube after you get it out. If Einstein hadn't developed the cosmological term, someone else would have. Because now, through the miracle of modern mathematics, we have a very different understanding. Through the miracle of modern mathematics, we can rewrite this equation. Now that's a small step for a mathematician, but a giant leap for a physicist, okay? Not that it's that hard to take that term and put it over there. That we can do. But you see, in physics, equations mean something, unlike in mathematics. And in this case, the stuff on the left-hand side corresponds to geometry. But on the right-hand side, to energy. So when we put that term over here, it corresponds to a new type of energy in the universe. And what could produce such a term? Only one thing. Nothing. And by nothing, I mean nothing. I mean if you take some space and get rid of all the particles and all the radiation and everything there, if that space weighs something, it will give such a term. Okay. Now that's crazy, of course. Empty space can't weigh anything. It's, you know, if you ask a 4-year-old, I was going to say if you ask Republican candidates, but that wouldn't work. If you ask a 4-year-old, what's the energy of empty space? They're going to tell you it's nothing, because, you know, there's nothing there. It's a good answer. Unfortunately, the 4-year-old hasn't taken quantum mechanics and relativity. Because you put those two things together, and it turns out empty space ain't so empty anymore. In fact, empty space is a bubbling, boiling brew of virtual particles popping in and out of existence in a timescale so short you can't see them. Now that sounds like philosophy if you can't see them, but it's physics, because while you can't measure these particles, called virtual particles, you don't see any of them, you can't measure them directly, you can measure their effects indirectly, and that's what this image shows here. This is an actual calculation of what the space inside of a proton looks like. It's a calculation was shown at the Nobel Prize ceremonies about 7 years ago by the people who developed the theory that allowed us to calculate what the space inside of a proton looked like. These fields here are popping in and out of existence, and they are relevant to your life, because you may have learned in high school that protons are made of particles called quarks, 3 of them. But it turns out if you add the mass up of those quarks, they only add up to 10% of the mass of a proton. 90% of the mass of protons and neutrons comes due to the effect of the energy of these virtual particles. And since they make up your body, 90% of your mass is due to these things. And you wouldn't be around if it wasn't for them. So virtual particles really exist, even though we can't see them. Now, if we can do the calculation of how much energy they contribute to a proton, one of the most exciting calculations in physics we've been able to do, we can then apply the same reasoning and try and calculate how much energy these virtual particles should give to empty space. And when we do that, we go from one of the greatest calculations in physics to one of the worst. You can't see the 1 there, but we calculate that in fact the energy of empty space should be roughly a gazillion times the energy of everything we can see. And that's just impossible. If it was that big, then the universe would be expanding so fast, we would never have formed. This is indeed the worst prediction in all of physics. We come up with a number which is 120 orders of magnitude too large. Okay? And it's been around since I was a graduate student, and it was so bad we never talked about it. But we knew the answer, because we're theorists. We knew what the answer was. The answer was 0. It had to be 0, because 0 is a pretty number. But more importantly, you couldn't imagine calculating a number or canceling a number that's this big with another number leaving, say, something left over in the 121st decimal place. That's crazy. But you can make 0 really easily in physics, because you can have new mathematical symmetries that make exactly equal and opposite things, like the total charge of the universe cancels out and is exactly 0. So we knew that there was some new symmetry of nature that we hadn't discovered that would explain this, and we could go to bed at night. But the important thing is the universe is the way it is, whether we like it or not. Something I have to keep reminding people. It's vitally important to recognize that. And therefore, we may not, we may think the only sensible universe is one that has the number 0 here, but physics is an empirical science, and just hoping or arguing it's logical or sensible is irrelevant. What's logical and sensible is completely irrelevant. It's up to the universe to tell us what's logical and sensible, not to us, as I'll get back to when I talk about theology a little bit later. So we actually have to measure the energy of empty space. How can we do that? Quite simple. Because it turns out that, remember, the energy of empty space, if it has energy, it will produce a gravitational repulsion. That's what the cosmological term did. And therefore, instead of slowing down like any sensible universe should do, if it's dominated by the energy of empty space, it should be speeding up. And in 1998, 2 other groups of astronomers who didn't really know what they were doing, well, they knew what they were doing, they didn't know why. They were trying to measure the rate at which the universe was slowing down, because they wanted to determine exactly how much mass there was. And this was the cover of Science magazine, actually, in 1998. It may not look like much, but it changed the world. Because this is the Hubble plot that I showed you earlier, and we're looking to see if it's curving. And to see about that, I can just draw a straight line through that data set, bring the whole thing down horizontally. And if the universe were decelerating, as any sensible universe should do, all these distant supernovae should be found lying along this curve. But they're not. They're not even below the straight line. They're above the straight line. What does that mean? Well, one of 2 things. The data is wrong, which usually is, or the universe is accelerating. The expansion of the universe is speeding up. And if just for fun you wanted to fit and say how much energy would we have to add to empty space to fit that data, you get exactly what we're missing. If you put 70% of the energy of a flat universe into empty space, everything works. So that is the cockamamie universe in which we live. Completely different than we imagined before. 70% of the energy of the universe resides in nothing. 30% in some form of dark matter that's made of stuff different than you or I. And a bit of cosmic pollution that's left over to create everything we can see. So the first important lesson of this talk is you are far more insignificant than you thought. You can get rid of us and the galaxies and everything we see, and the universe would be essentially the same. So much for a universe that was created for us. We're relevant. Okay. Now, this is so important. It's changed everything, and it's the reason I wrote this last book, and it's given us clues that are amazing about a universe that could become from nothing. The dominant energy in the universe resides in empty space. We have no idea why it's there. And if anyone comes here at one of these lectures and tells you they know why it's there, they're lying, especially if they're a string theorist. Okay? Its existence is probably tried to the very beginning of time, and it will determine our future, as I'll talk about. Now, talking about our future, remember I got into this business because I wanted to know how the universe would end, and there's a simple way to determine it, using high school physics, or kindergarten physics probably nowadays. I don't have a coin here, but if I had a coin, you know, we can determine what's going to happen to the coin. I throw it up, it comes back down. I throw it up faster, it comes back down longer. I throw it up really fast if there's no ceiling, and it doesn't come down at all. How can you determine when something's going to escape the Earth? Well, it turns out we can do that, and all of you will remember this with fondness. It turns out the details are important, but we determined that there are two terms to the energy when I throw something up. There's a positive piece called kinetic energy, the energy of motion, and a negative piece that comes from the gravitational attraction. And we turn physics into bookkeeping. If the total sum of these two things is bigger than 0, this coin will escape. If it's less than 0, it'll return. So if the positive piece is bigger than the negative piece, meaning you make the velocity big enough, it'll escape. If it's not, it'll come back down. And when it's exactly equal, which is the escape velocity from the Earth, 11 kilometers per second, the object will gradually escape but never quite slow down and stop. So the interesting thing is that this applies not just to a coin, but to the universe. Because remember, here's the picture I showed you from Hubble, and if the universe is the same in all directions, then what will happen in any small region of the universe will happen to every region of the universe. So all you have to do, if you want to calculate whether the universe is going to expand forever, is ask what will happen to any given galaxy in a given region. Say we're at the center, we look out at that galaxy, and to determine if it's going to escape, we just calculate its total energy. Well, how do we do that? Well, there's a positive piece due to its motion. Well, that comes from the Hubble constant. We've measured that. We measured the expansion rate. We know how fast galaxies are moving. There's a negative piece coming from the sum of all the mass in the sphere attracting it. Well, we know that because we've gotten the dark matter. So we compare the two. And if B over A, if the negative piece is bigger than the positive piece, so B over A is bigger than 1, this will come back down and the universe will collapse. If B over A is less than 1, it'll escape. The universe will expand forever. Now, the amazing thing, truly amazing, is that B over A is nothing other than this quantity omega, which I showed you earlier. And we've measured omega. And therefore, if B over A is equal to 1, if we live in a flat universe, that means B is exactly equal to A. Well, if B is exactly equal to A, the positive piece is exactly equal to the negative piece, and the total gravitational energy of the universe is 0. And we now have discovered we live in a universe whose total gravitational energy is 0. Now, if you were going to create a universe from nothing, what would you make the total energy be? It didn't have to work out this way. But we have found, in fact, that the energy of our universe is, in fact, nothing. 0, zip. And this begins the saga I want to talk about in the last few minutes of this talk, which will last over the time allotted. But anyway. Nothing number 1. See, there's different kinds of nothing, I've discovered. Because, as I've tried to explain how you can get a universe from nothing, I get countered by different people, as you'll see. The first kind of nothing that you'd imagine nothing would be the nothing in the Bible or the ancient philosophers, where it's an eternal, empty, dark void. That's a pretty good example of nothing, right? But it turns out that kind of nothing is always unstable to forming something. Why? Well, first of all, that kind of nothing is full of virtual particles that pop in and out of existence. Well, they're not real particles, so that's not something. But when we allow them to have gravitational attractions, when we add gravity to the mix, then you can create virtual particles that pop in and out of existence. But if their gravitational attraction is strong enough, then the gravitational attraction has a negative energy, which counters the positive energy that it took to create them, and their total energy can be zero. And if that's the case, they will be produced and continue to be produced. And we are guaranteed in a universe full of empty space, if we wait long enough, something will arise, because nothing is unstable. So the first answer to the question, why is there something rather than nothing, is quite simple. Nothing is unstable. Now that should be satisfactory, but of course it's not, because that kind of nothing can produce something, and that bothers people. So I'm told, well, that's not really nothing. That's not nothing, because that nothing has space in it. It may not have particles, but there's space. And where did the space come from? So I say, okay, that's what, well, actually, I want to go back, because I want to make that point. You can create something from nothing in a universe full of space, and it was one of the biggest arguments why we couldn't create something from nothing, because something has energy. And it appeared to violate the rules. And the point I want to strongly stress is that a universe full of something can have zero energy. And therefore, there's no laws of physics that forbid creating such a universe. But now, let's get to a universe without space. If you add gravity to quantum mechanics, if you take a quantum theory of gravity, then instead of having virtual particles flushing in and out of space, you'll have virtual universes. Because gravity is a theory of space. And if space becomes a quantum mechanical object, it will fluctuate. And in a theory of quantum gravity, you're guaranteed to spontaneously create virtual universes that pop in and out of existence. Regions of space that literally didn't exist before. But that's not something, because those universes will collapse. It will disappear, just like virtual particles. Unless their total energy is zero. Now, the simple thing would be to say, look, we live in a flat universe that's got zero total energy. Well, unfortunately, it's not that simple. If it was, it'd be great, but I actually want to tell you the truth. We can't calculate the total energy of a flat universe, it turns out, because it's infinite, and there's a lot of ambiguities. The only universe whose total energy we know is zero is a closed universe. That we can calculate the total energy of, and we know it's zero. But we live in a flat universe, so what gives? Well, a closed universe, if you create it, of total energy zero, a closed universe will in general collapse, as I showed you. And it turns out if the closed universes you create are microscopic in size, in general, they collapse in a time of 10 to the minus 43 seconds. Much shorter than the length of this lecture. Okay? Or even how long it seems. The only way to make a closed universe to last long enough is after you create it, you put some energy in empty space and puff it up. Well, it turns out our fundamental theories of particle physics predict exactly that phenomenon. It's called inflation. But it's a real kind of inflation. We predict that the early universe actually increased in size by a volume of 10 to the 90th in a time scale of about 10 to the minus 30 seconds or so. And it turns out that that's not just a prediction. That's not just a random statement that we like to invent late at night. If you have such a phenomenon, if the universe at early times is governed by the energy of nothing, a huge amount of energy in nothing, well, it turns out there'll be quantum fluctuations in that nothing due to particles, virtual particles, and they'll get frozen in after inflation ends, after that energy of empty space goes away. And what kind of fluctuations will they produce? They'll produce little lumps. And the kind of lumps they'll produce are exactly the kind of lumps we see in the cosmic microwave background radiation. It agrees exactly with what we predict. If that's true, that really means we are all here due to quantum mechanics. All of the fluctuations, the little lumps that later produce galaxies and planets and people, started out as little quantum mechanical fluctuations. It's remarkable. But more importantly, when a universe puffs up, when a closed universe puffs up, just like blowing up a balloon, it looks flatter and flatter and flatter. And the prediction of inflation is that the universe, after the end of this period, would look to arbitrary precision flat. So the only kind of closed universe that could survive long enough for people to evolve in it and planets to form is a universe that's flat. And that's the one in which we live in. So if you were going to create a universe from nothing by quantum mechanics, the only universe that you could create from nothing that would live this long must appear to be flat. Exactly what we see. So our universe can come from nothing, no particles in space, no space. You think that would be good enough. But it isn't, because that kind of universe can come from nothing, and some people are bothered by that. So they say, well, look, no good. You don't have particles, you don't have space, but you got the laws. The laws, who created the laws? Well, let's dispense with that. Even the laws of physics themselves may be accidental, the last result of the last few years of physics. And to show you that, I have to show you one more figure, and then we're done with the figures. This is a brief history of time. This is the density of matter in the universe as the universe expands. It goes down. And this is the energy density of empty space. It remains constant because there's nothing to get diluted. And this is where we live now, we think, where the energy of empty space is about 3 times the energy of matter. Right there. But if you look at this picture, you should be disturbed. Because we live at a very special time. It's about the only time in the history of the universe when the energy of empty space is equal to the energy of matter. But Copernicus told us that's not supposed to be the case. Why 13.7 billion years after the Big Bang, this random time, should we live at the only time in the universe when those two numbers are about the same? Well, physicists have come up with a proposed solution. That is, that galaxies exist. Why is that the case? Well, let's say the energy of empty space were different. 50 times bigger, say. Well, these two curves would cross at a different time. What time would that be? Well, when galaxies first formed. But if the energy of empty space were bigger than the energy of matter before galaxies formed, then galaxies wouldn't form. Because the repulsive force would beat out the attractive force, and no galaxies would form. So people have recognized that maybe this is telling us something. And it's led to something I call anthropic mania. If there are many different universes and the energy of empty space can vary in each one, then only those in which it's not much greater than what we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because astronomers are here to measure it. And you laugh, it sounds ridiculous. But it may be true. It could be that, in fact, there are many universes, and in fact, the reason we're here is because we're here. It's like, I mean, to many people this sounds religious. It sounds like the universe was made for us, but that's not the case. It's more like a kind of cosmic natural selection. It would be very surprising to find ourselves living in a universe in which we couldn't live. We'd be very surprised, in fact. And so therefore, this tells us that it may be that this fundamental quantity, the energy of empty space, is just an accident. It's different in different universes, and live with it. It's very frustrating, except particle physicists have jumped on this, because particle physics is way ahead of cosmology. Because cosmology, there's one fundamental number we don't really understand, the energy of empty space. But in particle physics, there's many more numbers we haven't understood for much longer. We haven't understood why gravity is the weakest force in nature, why the proton's 2,000 times heavier than the electron, why there are 3 generations of elementary particles. There's a whole bunch of things we haven't understood. And particle physicists have jumped on this and said, look, maybe we don't have to understand anything. Maybe it's all an accident. Maybe all of these fundamental quantities are just accidental, and if they were any different than they are, then we wouldn't be here. And this means you don't need a theory of everything. You just need a theory of anything. And we have such a theory. It's called string theory. So I just want to show you one slide summary of string theory. One guy says to another, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. And the second guy says, okay, what would that imply? First guy says, I don't know. So that's the story of string theory for the last 40 years, okay? I'm being a little hard on it, but still, It used to be taught as a theory of everything, but the problem with string theory is it predicts a universe that has maybe 10 or 11 dimensions. We don't live in such a universe. So how can that be consistent with what we see? Well, a lot of dimensions, 6 or 7, would have to curl up. Well, it turns out there are lots of different ways to curl up those extra dimensions, 10 to the 500. And each different way you curl them up produces a 4-dimensional universe with different laws of physics. So in string theory, you predict not just one kind of universe, but maybe 10 to the 500. And one of them is guaranteed to have, if you think, the properties that we measure. Now, is that science? Probably not. Because if you have a theory that can be consistent with anything you could ever measure, it's not a theory. But whether we like it or not, it may be true. And if this is the case, it addresses that final problem. Because it means that the laws of physics themselves are completely accidental. They come into existence at the same time the universe comes into existence. And in that case, this multiverse, as we call it, many different possible universes, is very similar to the prime mover of Aristotle or the first cause of the Catholic Church. Because the big problem, the reason people want to have a creator or a mover is because we're told that every effect must have a cause. Every beginning has a cause. It's not true, but nevertheless, if it bothers you, you need something that's kind of eternal and outside our universe. Some people call that God. But the multiverse serves exactly the same purpose, but there's a big difference. It's well motivated. I mean that not facetiously. I mean it seriously, because when I've debated certain people, certain apologists, they say, well, you invented the multiverse because you didn't want God. That's not the reason we've been driven to it. We've been driven to it because the laws of physics, based on observation, have driven us there. It wasn't a philosophical prejudice that led us there. It was nature. So, the last thing I want to mention, and I will go 5 minutes over time, is because it's in deference to my late friend Christopher Hitchens, who I used to try and explain this to, and he pointed out to me that, and he was writing the foreword for my new book when he got too ill and wasn't able to complete it. He said, nothing is heading towards us as fast as can be. Because I said, what will the future be like? And the future is amazingly interesting and depressing. Because what will physicists in the far future see? In a planet around a star in a Milky Way galaxy 100 billion years from now or 200 billion years from now? Well, if the universe is speeding up, then all the other galaxies we now see will be moving away from us at faster than the speed of light by that time, which is allowed in general relativity. But when they are, they won't be visible. So observers in the far future will discover electromagnetism and quantum mechanics and general relativity. They'll build telescopes, they'll look out, and they'll think they live in the universe we thought we lived in 100 years ago. They'll see one galaxy, their galaxy. Outside of it, they'll see an eternal void, a darkness, an empty, what looks like a static universe. All evidence of the Big Bang will have disappeared for such observers. And eventually, the stars in our galaxy will die out, and the universe will become cold, dark, and empty. Nothing. So the simple answer in that case to the question, why is there something rather than nothing, is right simple. Just wait, there won't be for long. And again, I say that a little facetiously, and I don't say it facetiously because it addresses another incredible conceit that humans have. In biology, we seem to think we're the pinnacle of evolution, that it stops here. Of course, it doesn't stop. Life on Earth continues to evolve. We're continuing to evolve in our own ways. Similarly, people think the universe that we now live in is the pinnacle. It was all created for us, but the universe of the future won't be anything like the universe of the present. It's not at all the case. So in fact, that's the second lesson I want to tell you. First thing was, you are far more insignificant than you thought. And the second lesson is, the future is miserable. I think I'll skip Einstein versus God because he wins. I do want to end. And well, let me just point out. You can read this if you want. It doesn't really matter. The story I presented to you today does not say that the universe came from nothing. It says that it's plausible that the universe could come from nothing. And that I find as remarkable, unbelievably interesting, and amazing that we've gotten to the point where, in fact, we can imagine a plausible series of steps by which nothing can become something. It's kind of, and Richard Dawkins was kind enough to write the afterword for this new book, and he was very kindly compared the new book to The Origin of the Species, which I thought was a little extreme. But still, in spirit, there's something there, because what Darwin did was say, before Darwin, life was a miracle. The diversity of life on Earth had no explanation. And what Darwin showed was a plausible mechanism by which the diversity of life on Earth could occur. He didn't know about genetics, he didn't know about DNA, but he showed plausibly how it occurs, and now we know. We are now at the stage in cosmology where we can have a plausible mechanism by which the universe can come from nothing without any divine intervention. Doesn't require it, but it's plausible. And as my friend Steve Weinberg would say, science doesn't make it impossible to believe in God, it just makes it possible to not believe in God. And the multiverse, as I point out, and the argument I give is a lot stronger in the end of the book, says to me that God is unnecessary or at best redundant. And I find that remarkably satisfying. So let me conclude. Science has demonstrated that a universe from nothing is not only plausible, but the other thing is it's likely. Because if you wanted to describe the characteristics of a universe that would come from nothing, it would have precisely the characteristics of the universe we measure. But more importantly, what we mean by something and nothing, as I said, has completely changed from the time the classical philosophers and theologians first raised the question. So I'm often told, you're not addressing the philosophical nothing. And my answer is, who cares? The philosopher's nothing is irrelevant. It's the physicist's nothing that matters. The question, why is there something rather than nothing, is not the interesting question. The interesting questions are, how did the universe form, evolve, and how can we find out? Those are the operational questions. Those are the things that matter, not stale old philosophical issues. And those are the questions we are trying to answer right now, and we have come up with the most amazing discoveries. It's worth celebrating and worth sharing. So in fact, you know, I told you that you're insignificant and the future is miserable, but you shouldn't be depressed. You should be excited, because we're here at this random time in the middle of nowhere, and we've evolved a consciousness that allows us to appreciate these amazing facets of the universe, and instead of being depressed, we should make the most of our brief moment in the sun. But if you want to think of the future, here's something that may make you a little happier. The future will be such. In the future, we'll be lonely and ignorant, but dominant. And those of us who live in the United States are quite used to that. Thank you very much. They're still here. Wow. I didn't expect that. Thank you for staying, most of you. So I have some questions, yes. Okay. Okay, we'll start here.
So you just mentioned that in the particle physics, there are many like gravitational constant or some other fundamental constants.
Yeah.
And we don't know why they take these values.
Yes.
And in this multiverse scenario, how did you, I mean, you mentioned that maybe in the other universe they could take other values, but how do you prove this? I mean,
well, okay, the question, I repeat the question, right? So the question was, look, in particle physics, we've argued that there could be many universes and the fundamental constants take different values. And in the multiverse, I've argued that that happens. How can we prove that?
Or how do you prove in the other universe they take different?
Well, the first case, there are a number of different possibilities that produce a multiverse. The one I showed was from string theory, but it turns out inflation also produces a different kind of multiverse. But let me just take the string theory example as one example. There you can actually, in certain cases, mathematically calculate what the forces, which forces will exist and what the spectrum of particles would be mathematically if you so-called compactify these extra dimensions. And so you can look for 11-dimensional universes that compactify to 4-dimensional universes that have 4 forces left over, which is like the ones we see. You can look for ones that may have 3 generations of elementary particles. But you'll see that each different way you do it, you'll end up with different spectra of particles and different forces, which is how we know that the laws are different. So we can show mathematically that in those universes, each compactification will produce a different set of laws of physics. The nice thing would be to do, which they haven't been able to do, and it would make it exciting if we could, is if we somehow found that probabilistically, you know, you could show that every universe that had 4 forces, in this case, also had a spectrum that was like ours and also had an energy density that was like ours, and that would give you great confidence that maybe this picture worked. but no one's been able to do that mathematically yet. So it's just a speculation. But at least we know that if string theory describes reality, and there's no evidence that it does, I want to emphasize that. There's no evidence that there are extra dimensions. There's no empirical evidence that string theory is anything but a mathematical idea. But it's a well-founded one. If it was true, then we have good evidence that the laws of physics are accidental. And I won't go in. It turns out inflation gives another argument for why that would happen in a very well-defined and even more calculable way. But since the picture I showed was some string theory, that's the one I'll give you. Take a few more questions. Should we take one from the back? Way in the back. Way over there. Yeah, you. Yeah, you.
What is the most important property that makes a universe observable?
Light. What's the most important property that makes the universe observable? Seriously, for us it is that we can detect photons, for the most part. But what's really neat is that we don't need to detect photons to detect the universe. We certainly don't need to detect visible photons. What is one of the reason all of this is possible is because every time we open a new window on the universe, we're surprised. That's why it's worth building new windows, like the James Webb Space Telescope or gravitational wave detectors. Because what we find is visible light is just a tip of the iceberg. We build X-ray telescopes and infrared telescopes, and we use all of them to expand what we can detect. And then we build detectors that might eventually detect gravitational waves, which will be the future. Because then we'll be able to detect waves that came not from when the universe was 100,000 years old, but we'll be able to detect signals of when the universe was a millionth of 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 a second old. So we just expand our eyes by finding new ways to detect things which were previously invisible before. And I think that's why we ask, why should we build these things? Or the Large Hadron Collider, which allows us to observe the universe on scales so small we never could have seen that way before. And the answer is, if we stop doing that, we'll stop asking questions. And you know, people often say, but why should we spend money on this? I mean, I am the first to say that every bit of my research has absolutely no practical value whatsoever, except for understanding where we came from. And to me, if you stop asking those kind of questions, what's the point of being around? I mean, it always amazes me when people say, ask me, well, what's the purpose of what you do? Well, make a better toaster. Well, have a faster car. But they never ask that of Mozart or of Picasso. You know, why make a painting? Why make a beautiful symphony? The answer is, it's what makes being human worth being human. Okay, anyway. I should end there, but I'll have to think of something else profound. I think I'll take 2 or 3 more questions. Okay, you there, in the center.
Could you talk about the Higgs boson within all this?
Yeah, I haven't mentioned the Higgs boson, which of course is of great interest to people because that's one of the things the Large Hadron Collider is being built to detect. The Higgs boson relates to another kind of remarkable cosmic accident. And it really is. I told you quarks have mass, but they don't account for the mass of the proton. But where do they get their mass from? Well, it turns out our ideas based on experiment are really remarkable. They say that all elementary particles actually have no mass whatsoever. But what happens is there's this background invisible field permeating all of space, and it's kind of like trying to swim through molasses. Elementary particles are moving through that. Some of them interact more strongly with that field and have a greater resistance to their motion and act heavier. And other ones interact with it more weakly and act lighter. So all mass, which is responsible for our existence, is just an accident of the fact that this field formed. Well, it sounds nice, but how can you know that? Well, if you smash empty space with enough energy, you excite this field, and you pop out real particles that are associated with this field called Higgs particles. And we think that, in fact, we can smash empty space, if you wish, hard enough with the energies we've got at the Large Hadron Collider to produce these real particles. And if we do, and in fact, as you probably know, there's tentative evidence announced a few months ago at CERN that we've discovered the Higgs boson. If that's the case, to me it is absolutely amazing, because it's this theoretical edifice we built up over 50 years without any direct evidence for this idea. And it would be true. And it is, if you're a theoretical physicist and you're sitting in a room at night, to think that something you develop might actually relate to the real universe and is actually there is terrifying. And it will really be amazing if it's true. I will be surprised because, again, if you're a theoretical physicist, the most important two states to be in, as I often say, are either wrong or confused. Because it means there's more work left to do. And most of our ideas are wrong, which is why it takes time and effort. And this would be amazing as if this idea we've developed is actually true, but it seems to be true. And we'll know within a year. At CERN, they'll be able to redo the experiments with better accuracy and know if the particle they discovered is the Higgs particle. And it really will mean that we've answered this profound question about the universe, which is why elementary particles have mass. And it would be amazing, truly. Okay, I got to pick two more. I'll take one in the back, way over there, and then one in the front. Yes? You over there, yep. Yep?
As sentient beings that have self-awareness, how, as a theoretical physicist, do you how can you explain consciousness and what a scientific consciousness is?
Okay, well, the question is, as a theoretical physicist, how can I explain consciousness? And the answer is, I don't have to. That's why I'm a theoretical physicist. I'm not a biologist or a neurologist or a psychologist or a philosopher. Consciousness is really hard. And I mean, the institute that I run, one of the things we're worrying about is development of consciousness, but it's a really hard question. It's much harder than understanding the universe, and that's why I do the easy stuff. Okay. Yes, last question.
If the universe is expanding and there's more nothing space, why isn't more stuff being created? Like the same as how the universe started.
Okay, if the universe is expanding and there's more nothing space, why isn't there more stuff being created? Well, the answer is that, that creating stuff takes a long time, first of all. The fluctuation, or whatever it is that produced our universe, produced a whole space, okay, that was incredibly dense and incredibly hot. That kind of thing should happen very rarely, okay? But the other thing is, it could be happening right now, all around us. Because you see, it's hard to think of space where there was no space before. It's a hard concept. But if we are creating new universes, not we, but if nature is creating new universes, it's creating space where there was no space before. So it's not space in our universe, it's a whole new universe. A universe that becomes, in fact, from the outside it would look like a black hole, a microscopic black hole. It would shrink down, and from the inside it would get bigger. But it would quickly remove itself from our horizon. So it's a space that you're creating universes that aren't part of our universe. So it's not too surprising you don't see them. Okay? And that's perhaps a good confusing way to end this lecture. Thank you very much. Thank you. Thank you very much.